All right. Well, greetings, everyone. Thank you for joining us today. My name is Adam Maxwell, and I'm a member of the IEEE-UFFC Society's Education Committee. It's our pleasure to host the 5th webinar in the virtual lecture education series. So these lectures present an opportunity to our members worldwide to learn and interact with our distinguished lecturers, star ambassadors, and other members of the community. You can find and register for the future lectures on the upcoming events listed on the UFFC Society's homepage online. Just a few details on today's seminar. You can type the questions that you have by using the chat function anytime during or after the lecture, and these will be addressed in the following question and answer period. The entire session is recorded and placed on the Society's YouTube channel for review and for those who are not able to join us today. Please also keep an eye out for an email after the lecture with a very brief survey to share any suggestions or feedback that you might have about the lectures. And finally, a huge thank you to the members of the Education and Lecture Series committees, as well as our student representatives for their efforts in launching this program. In particular, I'd like to thank Stephen Lee, Ro-Chen Liu, and Molly Bracken for their help organizing the lectures and with video editing and captioning. So with that, I'll turn this over to our moderator, Philip Fang from the University of Florida, to introduce our speaker.
Hi, good morning. Thank you very much, Adam. Can you hear me? So it's my great pleasure to introduce today's speaker, my colleague, Professor Joe Harley. Professor Harley is currently an associate tenured professor in the Department of Electrical and Computer Engineering at the University of Florida, Gainesville. His research interests include the integration of numerical and analytical models with machine learning and data science for smart infrastructure monitoring and material characterization. Professor Harley is a recipient of 2021 Achenbach Medal from the International Workshop on Structural Health Monitoring, a 2020 IEEE-UFFC Star Ambassador Award, a 2020 and 2018 Air Force Summer Faculty Fellowship, and a 2017 Air Force Young Investigator Award, and earlier a 2014 Carnegie Mellon A.G. Jordan Award for Academic Excellence and Exceptional Service to the Community. He has published more than 90 technical journal and conference papers, including 4 best student papers. He's also an associate editor and member of the editorial board for Structural Health Monitoring International Journal, and a member of the editorial board for Ultrasonics, and a member of the IEEE Ultrasonics, Ferroelectrics, and Frequency Control Society, basically UFFC, the Technical Program Committee, and a member of the IEEE Signal Processing Society, and a member of the Acoustical Society of America. So without further ado, Professor Harley, please.
Hello, welcome to my talk. I am Joel Harley. I'm an associate professor at the University of Florida. I'm also the director of the Smart Data Lab. And today I'm going to talk a little bit about physics-informed guided wave ultrasonic machine learning. Now, before I do that, I want to first acknowledge all of the students in my lab who have really helped make my lab what it is today and have done a lot of this research and have really, they're the drivers of all this work. So they really do need to be appreciated. And specifically, I want to point out my graduate students and my postdoc who have done a lot of this work. And particularly in this talk, I'm going to highlight the work of 3 of my PhD students. 2 of them graduated. So Preet Auguri is the first one. Shrustabetti is the second one, and the third one is Harsha Titali. So the three of them are the masterminds of a lot of this work, and a little bit of it is from my PhD as well, in fact. So my lab does a lot of different things. We have a lot of interest in a lot of different topics, but one of the things that kind of a lot of our research is focused on is this idea of models, and models being imperfect. And this started when I was a PhD student. I am an electrical engineer and a signal processing person, and that got me into machine learning really, but a signal processing person by expertise and training. And signal processing is very interested in models, specifically statistical models, but I worked with a lot of civil engineers who were experimentalists. So we had my advisor who was very much, oh, statistical models are very important, we got to use them. And I had these civil engineers that I worked with that said, oh, don't worry about models, just look at experimental data, understand the experimental data, and that's all that matters, because the models and the experimental data will never match. And this got me really interested, particularly once I started becoming a faculty member. You know, why can't we really use models for data analysis? I do data analysis, and usually the answer is they just quite aren't close enough. So let me give you an example. So I do a lot of my work in guided wave structural health monitoring. That's what this talk is about. So in guided wave structural health monitoring, the general idea is we have some kind of structure. Let's assume that it's, say, an aircraft panel. Guided waves are transmitted out of sensors on the structure. They transmit through the structure, and they interact with some flaw or some damage, as we can see here. And guided waves are very nice because they have low attenuation. They're very sensitive to most kinds of damage. And it's pretty easy to implement. You just need some piezoelectric sensors to transmit some signals. The big challenge is the complexity of everything, because the ultrasonic signals are not just received at we don't just see the flaw signal, we also see signals that go from our initial transmitter to all of our other sensors or receivers, and we get all these reflections. And on top of this, we have multimodal and dispersive propagation, which I'll talk a little bit later. All of this makes wave propagation very complicated, and it's very complicated for us to really understand and interpret what's going on. On top of that, the signals are changing constantly over time. So this is an example of a signal, and we can see it, constantly changing due to environmental effects, temperature, weather, and the likes. And while it may not seem like a lot of change to you, what we see here is actually a whole lot of change, because these very fast vibrations shift a little bit, and it causes the entire signal to look completely different to most methods we use on a computer to determine if one signal and another signal are the same or different. So this is a big issue. So overall, what we need to do with our data processing is we want to remove all these remove the strong direct in multipath signals so that we can only see what we get from the flaw. We can retain the flaw signals, and we want to be able to interpret and understand what's going on over periods of time. So one possible solution to this is to use simulations, to use models, numerical simulations. So we can model how waves propagate. It's just the wave equation. And we can compare our experimental data to those simulations. And while this seems really nice and a great idea, it's very difficult to do in practice. And here's a simple example. So this is a data set that is courtesy of Karolecki at NASA Langley. And in this data set, this is basically a validated wave field. So the data set, it has experimental data on one side. So this is experimental data and simulation data, which we're trying to show that these two are validated. Basically, they're showing the same thing. And if you look at this as it propagates out, we see that we have some slight differences in the center. There's an actual transducer in the middle of the experimental data, but they look pretty similar. Visually, they look pretty similar. However, if you ignore the center data, where they're quite obviously quite wrong, the accuracy between these two, based on a correlation coefficient, is only about 18%. And 15% is not enough to really do any kind of data processing, right? That's 80% wrong. So if I do something like a subtraction between these two, it won't look anything correct. So I can't use this information, even though this is a true validated simulation observed. If I look at it, it visually looks correct. So we need higher standards in order to do data processing. So the question is, how can we improve these models? How can we improve these models through the use of experimental data? And that's what I'm going to talk about. I'm going to talk about 3 different approaches that we have taken to try to answer this question. How do we improve models with experimental data? And we're going to look at 3 different kinds of models. So our first kind of model is going to be physics-based models, which physics-based models are great. They're extremely generalizable, right? Wave equation is a great example. There are millions and millions and millions of ways we can change the wave equation by changing boundary conditions and whatnot, that we can produce any kind of simulation. However, it doesn't really specifically mean anything. We need lots of different parameters and knowledge to make the physics-based model work. On the other end, we have experimental realizations, and that can be thought of as a model, right? I collect a baseline measurement from an experiment. That is a model of sorts. And that represents what data can be. But, all I get is the experimental realization. I can't change it. I can't make it more flexible because that's all I have. And then we have this in between, which is what I would say is our machine learning models. These are learned models, computer models that can take in data and spit out models of what we believe things should look like. And they're kind of in between of these because they require us to train them usually. So that requires data. And that links us to a specific experimental realization of some kind. But they also are more flexible than the experimental realizations. So this idea is we can combine these types of models to create these kind of data adaptive models. So the first thing I want to talk about is something that links physics-based models with experimental realizations. And I will call this a model fitting paradigm. And this work started with my PhD with sparse wave number analysis. And Shrew Sabeti, my PhD student, did a lot of the work beyond that. So I want to talk a little bit about this, and this will build into the otherness that we talk about. So first we have to understand ultrasonic guided waves a little bit. So ultrasonic guided waves, we have some structure. Usually we're talking about a plate. We have 2 transducers on it, and a wave travels through this structure. From a cross-sectional point of view, what effectively happens is we have a wave that travels through this plate. It reflects off of one boundary, and then it splits off into longitudinal and transverse waves, both which have different velocities and thus different indices of refraction, or reflection in this case. This is by reflectance. These then split off and split off and split off, and we get this very complex set of waves as we get far away from our original receiver. And from a signal point of view, if I were to transmit an impulse, getting an impulse response, what we would get is a signal that looks kind of like this, where we see distance here, r, and so the r is the distance between our transmitter and receiver, and we see this very, very, very complicated signal that becomes very, very difficult to really understand and interpret. So the impulse response is complicated. We can take this, and in the frequency domain, so we're now in omega here, in the frequency domain, we can represent this by this equation, roughly, where we have a sum. So we have the sum of n modes, so different modes that change with different, have different velocities at different frequencies, multiplied by our transmitted signal, the frequency response of that particular mode, which we don't usually know, multiplied by a complex exponential with the wave number function, multiplied by travel distance. And this is basically a plane wave. And we have an attenuation term based on geometric spreading. So basically we can model our waves as some kind of plane wave based on 2 points, a transmission and a receiving location, with a whole bunch of parameters that we do not know. And the wave numbers themselves are represented by what we call dispersion curves. So these are the dispersion curves for waves in a plate called Lamb waves. And we can see here we have these individual modes. So there's A naught, the anti-symmetric mode, the symmetric mode, anti-symmetric mode, the 0th and the 1st, and so on and so forth. And basically what this means, if you look at these, if I have a signal at, say, 800 kilohertz, that means I have 1, 2, 3 different modes, which means my 800 kilohertz signal splits off into 3 signals, each that travel with different wave numbers or different velocities, and will have different amplitudes and different characteristics. So the modes make this quite complicated. Also, on top of that, we have these wave numbers. So if I transmit a signal, I'm usually transmitting a collection of frequencies. And we can see in some of these regions, the velocity, which is related to our slope here, the velocity is going to be different at different frequencies, and that's known as dispersion. So different frequencies are going to travel at different speeds. So this is K, or this is K, the dispersion curves. So one way that we can get about characterizing this for a data analysis perspective is by taking all of this theory and turning it basically into a linear equation. It turns out that's not super difficult. What we can get is we can have a matrix over here. So this is a matrix of frequency domain measurements. So these are all of our measurements that we might collect experimentally. We can take the Fourier transform of all of them and put them in this one matrix. We have what's called a propagation matrix. So this is our plane wave with our attenuation term right here. So this represents that equation that we just saw, and we can propagate this or create that. And then we have this matrix V, which is our frequency wave number representation, which is effectively our dispersion curves. And what these give us is they tell us at what values of K we have modes. So most of these values are 0 because that represents most of those values. There are no values K. And we get frequency on this axis. So, and that frequency corresponds to the Fourier transform over here. So effectively, this gives us the dispersion curves. On top of that, we also get amplitudes. So all of these values have different amplitudes, which gives us the transfer function for our waves, for each mode of the wave. And in total, you know, when you put this equation together, X is known, that's just the experimental data we collect. Psi is known, that's just a simple matrix. And V is the only thing that is not known. So we have a nice setup where we have a linear equation and we solve the linear equation. The biggest issue here is that N, the number of the size of our dispersion curve matrix of V, is usually going to be much larger than M, the number of measurements we have, because we don't know what modes we're looking for necessarily. Fortunately, V is sparse, so there's only a few values, few wave numbers that are non-zero. And it turns out that we can use this fact to solve this inverse problem. So effectively, this is what it looks like. We have some kind of analytical model. It doesn't necessarily have to be what I just showed you, but this is where we will start. We have an analytical model. We feed this into a sparse regression algorithm along with our data. And so sparse regression is finding the solutions to a sparse inverse problem. And then we can take the results, which give us dispersion curves, and perform detection, localization, or characterization with that. So here's an example. And I should note, we call this process sparse wave number analysis because we're finding the wave numbers that are sparse in the dispersion curves. So here's an example. I have 50 pixels, 50 measurements really, over time of waves traveling in a wave field. And you can kind of see here the values going up and down, and those the waves traveling, but it's very difficult to see what exactly is going on. So we can collect these 50 time measurements, estimate dispersion curves by solving this sparse regression. And what we get is something that looks like this, where we get these two prominent modes. There's a little bit of noise down here where we don't really have any real modal information, but we get a very nice representation. What we can then do is, because we know these dispersion curves, going back to this equation, right? We know V now. We can create a completely new phi to generate X, right? We can predict what X is going to be by generating a new phi for our V. So we do that. So we can create now a phi that allows us to predict waves at all of the other locations in this spatial region. In this case, we'll produce 40,000 pixels instead of our 50,000, or 50 pixels, yes. So we do that multiplication, and this is what we end up getting. And you can see the waves now traveling very, very nicely going down. And in total, we get a 99.6% match with the true wave field, even though we had originally 800 times less data than we're seeing now. And so this is showing the strength of just taking a straight up physical model, taking the data and doing a smart inversion. The sparsity is important in this case to get a result that allows us to do this kind of interpolation and extrapolation. We can do more with this. We don't just have to predict where the waves are traveling. We can also predict, how the waves will react to something. So we can say, oh, I have a scatter at some point potentially. So I may have a scatter right here. And we have some assumptions on how the waves scatter, but we can now predict what happens if there is a scatter there. And then we can do that all across the region. What if there's a scatter here? What if there's a scatter here? And we can use that as a means for locating damage. So this, for example, is the typical approach known as delay and sum that is used within the guided wave community to find damage with guided waves. And for this particular example, it doesn't do very well. In fact, it does very poorly. So the large value is usually indicating where the damage would be. So that would be right here. We can't really see it. This real scatter is in the center. Whereas if we use our method, this is the result that we get. And this is due to us utilizing all of the complexity of the guided waves. Delay and sum is a very simple approach. It takes the envelope of signals and basically just tries to look for where all of the values are large corresponding to this location. Whereas we use the entire signals, all of their dispersion, all of their frequencies, all of their modes. And we can get much, much better results than otherwise you could get. So what about other types of propagation? What about anisotropic propagation, for example? So anisotropic propagation occurs in composites. And we see it quite a bit in guided wave signal processing. So we can set up a different problem. So this is the problem that we had before. We can use a different model. And I won't go too much into this model, but basically it now gives us a three-dimensional frequency wave number representation. We have two wave numbers, a wave number for the x direction and a wave number for the y direction. And these are combined in such a way that produce an anisotropic representation. So we can take this anisotropic representation and repeat the same process. So this is another example where I have 36 pixels now, and there's a wave emanating from the middle of this. And you can kind of see something happening, but it's really difficult from these 36 measurements that we have. We produce a dispersion curve that looks like this right here. In this case, we only have one mode. And from that, we can do a similar prediction. In this case of 149,000 pixels roughly. And this has a match of about 88%. So this is the two compared with one another. We're actually missing one of the modes because it's very, very weak. And we're missing some of the reflections, but it's a very, very close match between the two. And this we could use for data analysis because, right, before we were looking at a 20% match, and this is now an 88% match, which is much, much better. What about other incomplete information? So this is another example. This is a spatial temporal sparse wave number analysis where we don't necessarily know, where we have randomly sampled locations basically in both time and space. And so you can see now, you can see the wave here, but we have actually a lot less data because it is randomly sampled in time and space rather than having a lot of data over time, but sparsely sampled over space. And so we can build a new model for this, which I won't go into. It gets fairly complicated. And in fact, we have now two matrices instead of one, two phi matrices, but the dispersion curves are still the same thing in the center. So, and this is what we get. So we have our sample data on the left-hand side. We have the true data next to that. We have our reconstructed data after that, and we have the subtraction of the two. And we see that we do quite well between the subtraction. We have a little bit greater error around the boundaries, but otherwise it looks pretty good. So sparse wave number analysis, it has a lot of good strengths. It can learn frequency-dependent wave propagation, doesn't require many measurements. In fact, we could probably go less than we are showing here. It can do interpolation, extrapolation, and can be adapted by changing the models in many situations. The limitations of it, though, is it's pretty strict on geometry. Your model has a particular geometry, and if the data doesn't follow that geometry, it's not going to work. Similarly, if you have inhomogeneities, or if you have reflections that aren't in your model, or you just can't figure out how to mathematically express them, it's not going to work. So we wanted to address those limitations. So to address those limitations, we looked at a method known as dictionary learning. This kind of removes the physics and only focuses on learned models. So these learned models are then combined with experimental realizations. So I'm going to talk about dictionary learning here. So dictionary learning actually has a very similar setup as our previous physics-based model. We still have a linear model, x equals phi v. V, I'm going to still say, is the dispersion curves, although physically I can't quite claim that it's dispersion curves because there's no physics in this, but it's going to act something like the dispersion curves. And then there's phi, which I don't know. So instead of defining this from physics, we're going to learn phi from either simulations or data. But otherwise, it has the same structure, right? Because V is still going to be sparse in this case. So how this works now is I have, this is a process known as transfer learning, basically. I have a machine learning method from which I learn from, and then I transfer that over to some other learning process. In our case, we have dictionary learning as our first task that we learn from. We input our data, which comes from basically a surrogate waveform. And this surrogate waveform can be from other experimental data sets, or it can be from simulations. We compute the dictionary, which is basically how we represent everything. That's our phi matrix. This gets passed on to our dictionary D, gets passed on to our optimization, our other learning framework, which is still sparse regression. We input our test data and our new wave field into this with our new dictionary D. That's our phi matrix. We put this into, again, our processing, and we can do wave field prediction or wave field damage isolation in this case. So let's show how this works. So I have a simulation here, and it's a very dumb simulation. It's just a wave traveling across the screen. It's pretty much just an impulsive plane wave. So it doesn't really match experimental data at all. But the key here is it has a geometry similar to the data that we're going to look at. Actually, we've seen this data, so that we know where the transmitter is, and the wave kind of follows the same trajectory as what we see in the data. So from that, we apply dictionary learning, and we learn the modes or atoms, the dictionary. So this is the phi matrix. This is basically the columns of the phi matrix. And you can see this actually looks pretty nice because each of these modes or atoms represent different wave numbers. So it's learning that different wave numbers are important in this particular case. And this is what we transfer over to the sparse regression. So we then take our measurements. In this case, we have 36 points. We can again see the waves coming from the top left, traveling through, and we do our sparse regression like we did before. And we can come up with this new measurement. Now, one of the nice things about this is since we're relying on the simulation, If the simulation doesn't have damage in it, then what we predict is not going to have damage in it because we're learning the geometry from the simulation. So even if the test data does have damage, then we don't get damage in the predicted data. So we can call this a synthetic baseline. It's now our experimental data, but without damage, which means that if I have data now, the real data has damage, which I think we should be able to see. Oh, this is just comparing, sorry, this is just comparing the two. So this is just a good showing that they match very well. This one will show the damage actually appear. So in this particular case, we have an aluminum plate. This is now showing that we can do something with more complex data processing. So I learned new atoms, new columns of my dictionary from this, which look, they have different wave numbers again, but they have a very different geometry to them than we had before. And then we have a steel plate. So our surrogate data is not from a simulation. In this case, it's from an experimental data. And we have another experimental data of a steel plate, which has different velocities and also has damage in it. And we learn a synthetic baseline now for the steel plate, which doesn't have damage in it. Because if I take the difference between these two, it's not perfect, but we get, let's see if I can, yeah, you can kind of start seeing out, you can see the reflections coming off, which is a lot harder to see in the original. Again, not perfect, but it's assuming very little knowledge to get this kind of subtraction out. So the strengths of dictionary learning are, again, we can learn all these frequency dependent information. We can do complex information and as long as we have simulations of the geometric information, and we don't really require any prior knowledge, physical knowledge, which is good and bad to some degree. The limitations are, it's not really physically interpretable. And this was one of the biggest issues that we had. We would get these results and we say, oh yeah, it makes sense, but it's not really physics. And as a result, we can't really interpolate and extrapolate outside of what we train on. We can't utilize physics in the same way that we did with sparse wave number analysis. So that brings us to our last paradigm. So this was the transfer learning paradigm with dictionary learning. We now look at a physics-informed paradigm, which uses all three of these models, physics-based learned models and experimental realizations. And we have a physics-informed dictionary learning and a physics-informed matrix factorization. And I'll talk about the second one here. So the idea of this, and some of you may be familiar with the idea of a physics-informed neural network. This is a similar idea, but we're doing it all with simple linear models because we don't need non-linear neural networks to do this. Our problems are all linear in this case. And this has a lot of advantages from an optimization and interpretability perspective. But basically, this turns into, we're going to solve this equation here. It's a minimization. I'm going to briefly talk about what it is. We have D, which is our dictionary again, which is also the same as our phi from before. This is a linear basis of modes that are in our data. In this case, it will actually be modes, unlike our dictionary. We have X, which is our data, and we have V, which is our coefficients. Again, very similar to the process of what we had before. X is equal to phi times V. This is X is equal to D times V. We have N, which is the number of modes that we are going to learn. We're going to try to minimize that, keep that to as small as possible. We have a regularization constant, gamma, and there's a couple different ways that we have arranged this equation. This is one particular way. Just note, if you look at some of our papers, there are other ways to write this out. And then we have the Laplacian, which is the second derivative, basically, which interestingly, there's a lot of different ways you can represent the Laplacian in this linear algebra form. And then a matrix K, which represents wave number squared. And the important thing here is this equation here is basically the wave equation. It's basically a second derivative of our modes. It must be equal to, this is the modes multiplied by a wave number value. That is the wave equation. So basically all this is doing is it's finding D, It's finding all of our modes and the coefficients associated with those modes, that's V, such that they must satisfy the wave equation. That's the heart of what this optimization is. And this is challenging for a lot of reasons. One, this is a non-convex problem, so there's going to be many possible solutions that, if you just follow the trend down, you're going to find a solution. It's hard to find the global minimum in most cases. This is maybe not necessarily explainable, interpretable solution, how you get it. And boundary conditions can be an issue, which we actually haven't entirely solved. Turns out that recent results in optimization theory show that we can actually globally solve these types of problems, which is great. And through solving this, we found that our solution is actually very explainable, very interpretable, which is one of the reasons why this makes it much better than using, say, a physics-informed neural network. We really do understand how this works. So here's the general equation. And I've simplified some of these processes. I'm not showing you all of the equations and how they work exactly, so just so you know. But this is the general process. So we have a wave field, which you can see on the right. In this case, the wave field has 3 waves. If I stop it real quick, there was a region over here that has a different wave number. So we have inhomogeneities in our wave number. And we have 3 waves traveling from 3 directions with 2 modes. So this is the second mode. This is the higher wave number, lower speed modes. And you can see as it goes through this region here, the waves are getting distorted a little bit. And what we're going to do first is we're going to compute the f of t of all of this data at every point in space. And we're going to consider one frequency at a time. So this gets processed on each frequency one at a time. So this is what the wave field looks like at a single frequency. We then compute the eigenvalue decomposition of L, which is the Laplacian. That's our second derivative. And there's a number of different ways that we can represent this. This particular paper uses one particular way. I'll leave it at that. There's other ways that actually produce better results than what I'm showing here right now. And then we use the eigenvalue decomposition. Basically, the eigenvalue decomposition turns into a transform for the data. So we multiply that eigenvalue, the eigenvectors by our data, and that brings us into some wave number representation. So we have horizontal wave numbers and we have vertical wave numbers. So this is wave numbers in 2 dimensions. And we can see the 2 circles representing our 2 modes. So this is one of our modes, and this is our second mode. So we have a low wave number mode and a high wave number mode. It turns out that solving that long equation that we showed turns out to be exactly the same as designing an optimal filter. So we design a filter that has an optimal value of k, which is the optimal wave number. So this is a circular filter basically, and then an optimal bandwidth. So we first find the lower wave number mode and says, this is the first one that we'll choose. That turns into our filter data. So we basically filter the data through this, which we can see on the left, and then we compute the error. So we now have the error result, which now has primarily the higher wave number. Although there are some wave numbers at the lower end over here. We just can't physically see them yet. And then we do the same thing. We have now our transformed error data. We find an optimal filter, we find the optimal k, we find the optimal bandwidth, and now we find this. And we can see that we get this whole region, but we're missing this area where we have the distortions in wave numbers. It has a slightly different velocity than the rest of the region. So it's able to deal with inhomogeneities. We compute the error, and then we repeat this process over and over again. And the first 3 linear components that we get, you'll see look like this. And there's also a little bit of this low frequency component that's in here too. You can see it's a little bit weaker in this area. It's a little bit less obvious than the high wave number component, which we can clearly see right here. But these all get added together to become the full wave field of that frequency. And the estimates of these wave numbers are very close as we can see from the top. And if we put all of these together, the original signal and the reconstructed signal are very, very similar. And so this can be used to create dispersion curves, but now we can have dispersion curves within homogeneities with very complex signals. So this is an example of the true simulated, so this is all simulated data, I should note. The true simulated curves, where we have two curves of for representing the small region location and the large region. And this is what we get from our method. And we're actually missing one of the curves down here, and we have a little bit of error as we get to higher frequencies. All of this we've actually fixed. This is a little bit of outdated results, but our more recent results have fixed this. So they all match up very nicely now. And here's an example of us separating out these individual components. So these, we have the three learned components and the true wave field on the right. And you can see we nicely separate out the modes, and we nicely separate out this one particular region with these modes. And we can get that from all the different directions. And this requires very minimal physical knowledge. We're just saying nothing about the geometry. All we're saying is everything that needs to satisfy the wave equation. So the strengths of this is this has the potential to work with very complex data. We can collect physical knowledge about very complex things with very little prior knowledge put in. It can be done with interpolation and extrapolation, very much like sparse wave number analysis, because we have that physics, we have the wave equation, we just need to throw everything in there. So it can do a lot, and there's a lot that we still haven't published on, to be honest, which we need to work on. The limitations are, it's complicated. The optimization, we haven't published much on it because we've been spending a lot of time getting the optimization right and getting the optimization fast and working robustly. So it actually does work fast, it works robust, but it is complicated. And the one thing we haven't quite figured out is handling boundary conditions. That's the big issue that we still have. But it's very nice work. So what is next? I don't know. Lots of different things. As I said, we want to work on publishing a lot more of this. If you have questions about it, feel free to ask me. But the general conclusion is, models are generally imperfect. But there is a way to combine these models, these physics-based models, these learned models, and experimental realizations all together through machine learning, through data analytics, to create what I would say are better models, or ways that we can utilize these models for data processing. And that's going to make a lot of our engineering so much better. So if you have any questions, please let me know. Feel free to visit my website. If you have questions about any of this work, send me an email. I'd be happy to talk with anyone. Thank you very much.
Thank you so much, Professor Harley, for the wonderful talk. So can you, Adam, can you show the slides again, or someone show the slides? And I will start addressing, ask Professor Harley to address the questions. And you're encouraged, please type in your questions in the chat window. We already have several questions here. First from Payal Gupta. Say hi. How do you estimate dispersion curve? This means initial V matrix or not? I think that's a good question.
Yep, that's a good question, because I kind of glossed over it. So this question came up during the first part, during the sparse wave number analysis part. And basically for that, we set up a linear equation and we solve the linear equation. Although we don't just solve it as a regular inverse problem, we solve it as a sparse inverse problem because the dispersion curves are sparse. Most of the values in that matrix of V are 0, and a few of the values are non-zero. So we use a compressive sensing approach, or really, most likely you'll see it as a lasso approach. So we basically do a lasso regression on that, and that preserves the sparsity and allows us to solve it with having much more unknown parameters than data. potentially. So basically the answer is we do a lasso regression.
Thank you. So Payal, I hope that answers your question. If you are around, you can still maybe follow up if you have further questions. And let's move on to the next question by Hao Tian Guan. I think the idea looks similar to Cindy, S-I-N-D-Y. Earlier, sorry, there's a new question pushing the earlier question up. Hao Tian's first question is actually, thank you for the amazing talk. My question is that, do you find physics-informed machine learning hard to train? In other words, how long and how many iterations do you spend on training a model involving X, Y, and T? T stands for time.
Good question. So it depends upon which models you're talking about. I'll note, as I kind of noted in the talk, I try to make things easy for us. We're not using any neural networks because it's honestly not necessary in this case. And that's going to help a lot with the training. So the sparse wave number analysis and the dictionary learning are really easy to train. They're pretty much lasso regressions. One iteration, I guess it could be multiple iterations at optimization, but very straightforward optimizations. The physics-informed learning aspect, the last one, is more difficult. It doesn't take all that long, but there's some tweaking of regularization parameters and having an idea of where things could go wrong. And we've been, as I kind of implied, tweaking this optimization to make it as robust as possible to this. So in terms of length, it doesn't take long. It takes, 20, 30 minutes at most. In terms of getting it right, it takes a little bit of more time and understanding, and hopefully it will be robust once we release it. But that, yeah.
His follow-up question is, he said he thinks that the idea looks similar to Cindy, S-I-N-D-Y. Do you mind reminding me what's the difference?
Yeah.
So suggest if maybe you can share the relevant slide, because we only see this cover slide now.
I can share my slides.
Thank you.
I will share the slide. So for those who don't know, so SynDY comes from sort of the work on PDE discovery from data, which you have data, you set up a linear equation very similar to this linear equation, which is why I'm showing this. And basically it's set up so that your matrix here is a bunch of derivatives, usually that would represent the partial differential equation. And this is the sparse coefficients for this partial differential equation. So you're basically learning a partial differential equation. And SynDY has been applied to nonlinear dynamic systems. So it's similar, especially this, in that we're using similar sparse regression to solve the problem. I would say two significant differences are my approach, or our approach that we show here, is more specific to a specific problem. We're not just finding the partial differential equation. In some ways, we know the answer to the partial differential equation. We're finding the coefficients associated with that. But I would also say a lot of the approaches that I do have a focus more on dealing with the data than the data, the PDE data discovery works are. And this is actually true for a lot of physics-informed learning work. A lot of physics-informed learning kind of deal with more pristine data sets. Usually they're simulated, and they're trying to get the partial differential equations associated with it, or complete the equations. The data sets that I'm using tend to be kind of messy. I use a lot of experimental data sets. So there's a little bit more of a push to make sure that they're robust. And I'm not really interested in the the true differential equation. What I'm interested in are the parameters that will allow me to reconstruct the correct wave fields from them. So there's a lot of similarities, particularly with my sparse waveform analysis work, but I think philosophically they're quite different.
Thank you. I just want to quickly add on that. You said in the earlier one, the regression one, you don't have any neural network. And in the physics informed one, do you can you clarify you have a neural network or not?
There's no neural network there either. You could do it with a physics informed neural network, but in general, at least from my perspective, it's not necessary. We're dealing with all linear wave propagation. The value of a neural network is it allows you to do non-linear operations. So if everything's linear, you should do it with linear stuff. Interestingly enough, though, with physics-informed neural networks being a pretty hot topic, no one has really done any of the math or study of physics-informed linear learning with linear equations. There's really no papers on it. So we're kind of, even though it's, you might say, a simpler approach, no one's really studied it up till now.
Thank you. Next question from Stephen Milligan. Could you describe computation power consumption of this solution when performing inference or interference?
Yeah, it's a good question. I would say for pretty much all of them, it's pretty, compared with other modern day machine learning methods, it's pretty low on the power consumption. This was kind of asked. The maximum amount of training time is 20-30 minutes. So we don't need high level GPUs. In fact, I don't think we use any GPU power in this case. So I would say it's pretty low relative to other things that you see around.
Thank you. While we wait, you are still encouraged to type in your questions. If you don't mind, I have a couple of questions.
You missed one question by Daniak, I think, up a little bit.
Oh, yes. Daniak, Van Are. Thank you. This was a very interesting talk with very intuitive slides. Can you elaborate on the fact that use a homogeneous wave equation as regularization in your optimization for solving a wave field that contains scatters?
Yeah. Going to the equation. Lost my slides. Oh, I think I pulled up the wrong slides. Oh well, so I will just unshare that. So for the homogeneous, so we include the homogeneous wave equation, and then feel free to elaborate on that question a little bit, because I'm not entirely sure what you want me to elaborate on, but I will try my best. So we add the homogeneous wave equation to basically add this constraint of, we know, I like to think of it as kind of, we want to interpolate between points, right? I have a point here and I have a point here, and there is some sort of relationship between them. But in general, right, if we use a generic kind of approach for filling in gaps, right, there's a lot of in-painting techniques in the machine learning literature, things that you might see like in Photoshop to determine, oh, these colors should be here if I don't know what they are, or I'm trying to fill them in. Those exist, but they don't use any physics. So you could get a whole bunch of different things, especially if these points are very far apart from each other. So by adding in the homogeneous wave equation, we're putting in a stronger constraint that says between here and here, it has to follow the wave equation in some manner. So that allows us to add in this interpretability and interpolation between those points. And obviously it will need more than just 2 points. 2 points is not enough, but it will try to fill in all those gaps using homogeneous differential, the homogeneous wave equation. And that's the general idea of this approach. We need a lot less data than we would otherwise need because the wave equation is kind of telling us what other information is out there and what we need to use.
Thank you, Joe. So I want to quickly follow up from just in case the audience also have other hardware engineers like myself. Can you, for example, in your wave-informed results, you have the aluminum or steel plate, and you have identified an area of maybe suspicious defects. Do you, so in that simulation or in that computation, what is the physical system that you can go back and to check your simulation results? Is that identification of the area with defects correct with your setup?
So the very last one with the physics informed is currently simulation. We don't quite have the right experimental data for that. But the idea experimentally would be, I have a plate, which could be for an airplane, or it could be, you know, we could have a plate of a pressure vessel or something like that, in which we take these measurements. And the area that is the different wave propagation could represent, for metal, could represent corrosion, for example. So if corrosion occurs, it causes that area to have a thinner walls, which causes the velocity to change in that region. So we're interested in, can we find that region that has different wave properties? And with the physics informed learning, we have that particular data set because that can't be done with any of the other data, the other methods. The other methods have more strict models that would not allow us to account for inhomogeneities unless we really know where the inhomogeneities are. Whereas with the physics informed method, it extracts out those inhomogeneities. It finds that they also satisfy the wave equation. They just satisfy a different wave equation than everything else.
And so in the experimental setup, I'm talking about imagined experiment. We don't have to do real experiment. When you set up your system, do you assign different material property in that region, or how do you set up the device?
I would not know. So basically, we would just place the sensors all across the structure, the material. We would collect the data from all of these sensors, and we would make no other assumptions. So no other assumptions are necessary. I don't need to know what the material is at any point. I don't need to look at a particular material. The algorithm figures all that out for us.
Mm-hmm. I see. And next question is, have you, so this is in terms of spatial resolution, do you have any comment in this, either this plate or aluminum plate for aerospace application?
That's a good question.
It depends on the probing Lamb wave you use, right? What?
Yeah. So the resolution clearly depends upon the wavelength and the frequency that we transmit. But it's more complicated than that, especially once we start talking about machine learning methods. We can't just say, oh, the resolution is 1/2 wavelength or 1/4 wavelength. So it depends a little bit what technique that we're talking about. So in terms of the sparse wave norm analysis methods, we showed that we could use that to do localization, which was far below actually was about the resolution, the 1/2 wavelength resolution of the waves. In terms of I think the physics informed machine learning, there is some resolution issues, and that has to do with our boundary condition problems. Because at the interface between one material and another material, we basically have a boundary condition interface more specifically. And at that interface, the wave equation basically is no longer valid because we're transitioning from one wave equation to another. So that has some issues with the resolution. I don't have a good quantitative number for that, but so we can do pretty good resolution, better resolution, I would say, than most guided wave methods, because they don't utilize all of the different properties that we utilize. But I don't have good quantifiable numbers for you, unfortunately.
Thank you. So considering a very inhomogeneous system like the Miami apartment, for example, a large scale system with different materials, many layers or many stories, do you see this method gonna need to take a lot of more complexity, or how does it scale?
So that's an excellent example, and that's the kind of example in which why we've made this progress all the way up to the physics-informed learning right now, because of it deals with inhomogeneity. And this is a problem in the structural health modeling community in general. In the structural health modeling community, if you look at papers, most of us have a plate, often made out of aluminum, but it might be steel or something like that, or composite, and it's homogeneous throughout, except for maybe a defect, which you're looking for. And that's mostly what everyone deals with. Once we move to more complex geometries, much more complex homogeneous behavior within the waves, it becomes a lot harder, and not many people are working on those problems. There are clearly some, but it's a big challenge. So the physics-informed learning is kind of, from my perspective, the first step in my lab towards really being able to address those more complex physics going on and be able to analyze them and use them.
Thank you. I don't see, so we are about actually over 12 o'clock East time, and I don't see more questions in the chat window. Thank you very much, Professor Harley, again. And thank you all for coming. And I would also invite you to follow the announcement and welcome you to the next virtual lecture in this series, as shown on this slide. Thank you, Adam, for putting this up. I think this concludes our today's webinar. Thank you so much.
Yeah, thank you everyone for coming. If you have more questions, do not hesitate to contact me, email me. I'm glad to see all of you here. Have a great day.
Thank you, Joe.